Let's run through the list. Data exfiltration. This is usually goal number one, stealing sensitive stuff. Customer PII, credit card numbers, health records, financial data, trade secrets, intellectual property, you name it. This immediately triggers massive regulatory fines. Think GDPR, CCPA destroys customer trust, leads to lawsuits, and can kill a company's competitive advantage if IP is stolen. Data manipulation corruption. Attackers might not steal data, they might change or delete it. Imagine altering financial records for fraud, messing up manufacturing schedules, changing inventory counts, or just wiping critical tables to cause maximum chaos. This means immediate operational paralysis, huge recovery costs, and a total loss of data integrity. Privilege escalation. Now, if the login the vulnerable application uses has more permissions than it actually needs, which is sadly common, an attacker exploiting an injection can leverage those permissions. They might grant themselves debowner, create new malicious admin users, or even use system procedures like XPCMD shell to execute commands directly on the operating system, assuming SQL Server service account has those OS rights. Remote code execution, RCE. This is the absolute worst case scenario for the victim. If the SQL Server service account does have high privileges on the underlying OS, certain SQL injection techniques or successful privilege escalations can allow the attacker to run arbitrary shell commands. They can install malware, create persistent backdoors, use the compromised server as a beachhead to attack other systems on your network. They effectively gain full control of the server hosting your database. Game over. Denial of service? DDoS. Injection can also be used just to bring things down. Attackers can flood the server with resource hogging queries, create deadlocks on critical tables, or even just derop key database objects like tables or stored procedures. This renders the application unusable, causes significant downtime, huge revenue losses, and really frustrates your users. Reputational damage. Getting hit by a major data breach due to a preventable vulnerability like SQL injection. That's a PR nightmare. It shatters customer confidence, makes partners and investors nervous, and the damage to the brand can take years, if not forever, to repair. You become that company that got hacked. Financial loss. And the costs. The costs are staggering. You've got regulatory fines, legal fees from lawsuits and investigations, the massive expense of hiring specialized incident response and forensic teams, the cost of notifying affected individuals and offering credit monitoring, the cost of rebuilding or fixing compromised systems, plus all the lost revenue from downtime and the long-term impact of reputational harm. It's easily a multi-million-dollar disaster waiting to happen.
Right. Now, why does this hit home specifically for you, the senior database professional, the DBA listening to this? Because, as the source bluntly states, execute at skull string used this way offers no safety net. None. Whatever malicious code manages to get successfully stitched into that string and passed to execute will be executed, assuming the application's login has enough permissions. Now, you might be thinking, well, wait, shouldn't the application developers be validating the input? And yes, absolutely, 100% they should be doing that. It's critical. But relying solely on application-level validation is just inherently risky. Developers are human, they make mistakes. Validation logic can be flawed, it can be incomplete, maybe new vulnerabilities get introduced later during maintenance. From your perspective, guarding the actual data, allowing this anti-pattern is like installing a state-of-the-art vault door but then leaving a sticky note on it with a combination, just trusting that nobody naughty will read the note. You are the final guardian of that data, and this pattern effectively bypasses crucial built-in database security mechanisms designed to protect it.
Okay, so SQL injection is the headline-grabbing, potentially business-ending security threat. It's dramatic, it's terrifying, we get it. But the very same anti-pattern using execute with that unchecked string concatenation, it has another consequence. This one's often less visible in the short term, maybe more insidious, but it can be equally detrimental to the overall health and performance of your SQL Server instance. This is the problem of planned cache bloat.
That's right. While SQL injection feels like a sudden, violent attack, planned cache bloat is more like a chronic illness. It slowly, steadily degrades your server's responsiveness and efficiency over time. The source nails it, calling it subtle but equally detrimental.
Okay.
Now, to really get this, we need a quick refresher on SQL Server's planned cache. We all know it exists, but let's just recap. When you submit a T-SQL query after parsing, SQL Server sends it to the query optimizer. The optimizer's job is pretty complex, very CPU intensive. It analyzes your query, looks at available indexes, statistics, constraints, server resources, all that stuff. And it tries to find the most efficient way to get or change the data you asked for. The output of all that work is an execution plan, basically, a step-by-step recipe for the database engine. Now, because this optimization process takes time and eats CPU cycles, SQL Server tries to be smart about it. It stores these compiled execution plans in a special area of memory called the plan cache. The whole point, plan reuse. If the database engine gets a query that is identical to one it's already seen, compiled a plan for, and stored in the cache, It can often just grab that existing plan from the cache and start executing right away. This completely skips the expensive compilation step, saves a ton of CPU, and makes query execution significantly faster. Better server performance, higher throughput. That's the goal. Okay, but here's where execute at SQL string with those concatenated literal values just throws a wrench in the works. For SQL Server to consider two queries identical enough to reuse a plan, the query string passed for execution has to be essentially byte for byte identical to a string already associated with a plan in the cache. When you build your dynamic SQL by directly embedding literal values like mountain bike, road bike, gloves, or maybe different product IDs right into the query string before you call execute, well, every single unique value creates a syntactically different query string from SQL Server's perspective. Even tiny differences that a human would instantly recognize as the same basic query structure. Things like varying white space or, crucially, variations in casing for the same literal value, like searching for mountain bike versus mountain bike. The SQL Server, using this anti-pattern, those result in two completely distinct query strings needing two separate plans.
Right. So sticking with our product search example, if you're using that vulnerable, execute at SQL pattern and users search for different products or even the same product with different casing, you might end up executing things like execute and select product name, price from production, products where product name, mountain bike, then maybe execute and select product name, price from production, products where product name is mountain bike. And then execute and select product name, price from production, products where product name road bike, or searching for something else entirely. Execute, and select product name, price from production, products where product name gloves, or maybe by ID. Execute, and select product name, price from production, products where product getting 23 in coves. Even though the underlying structure of those queries like select the key, where product name, pryfleet, or selecting, where product some value is fundamentally the same in our heads. SQL Server actually receives 5 syntactically unique strings here. 5 different commands as far as it's concerned.
Exactly. And for each one of those 5 unique strings, SQL Server is forced to go through the entire expensive compilation process all over again. 1, it has to parse and normalize that specific unique string. 2, it has to run the query optimizer to compile a new dedicated execution plan just for that exact string. 3, and then it has to store this new unique plan in the plan cache. These plans, the ones generated for dynamic queries with hard-coded literal values like this, they get classified as ad hoc plans. Now imagine an application with even moderate traffic and lots of varied user input using this execute anti-pattern. The plan cache can just explode, getting rapidly filled with thousands, maybe tens of thousands, potentially even millions of these ad hoc plans. And many of them might only ever be executed once. That specific combination of values might never appear again. This is plan cache bloat. It's like trying to run a library efficiently when it's completely stuffed full of single-use flyers and pamphlets instead of reusable books. And the consequences of the severe accumulation of ad hoc plans, well, they're anything but subtle when you look at server health. They hit hard. Increased memory consumption. Okay, first off, each compiled plan takes up memory in the plan cache. Bloat means a huge amount of precious server memory is being wasted storing these unique, often single-use plans. This directly steals memory away from the buffer pool. That's where SQL Server caches actual data and index pages from disk. When frequently accessed data pages get pushed out of RAM because the plan cache is bloated, SQL Server has to constantly go back to disk to read them, physical I/O. Disk I/O is orders of magnitude slower than RAM access. Your storage subsystem starts thrashing, and data retrieval slows down across the entire server. Higher CPU utilization for compilation. The server ends up spending an excessive amount of its CPU cycles just parsing, optimizing, and compiling all these new, unique plans instead of actually executing queries and serving data. This becomes a massive, unnecessary CPU overhead. Picture your server's cores running hot, maxed out, just trying to figure out how to run queries, leaving less CPU power available for the real work of processing data. This absolutely cripples your throughput, reduced cache efficiency. A bloated cache is, by definition, an inefficient cache. Like that flyer-filled library trying to find a genuinely useful, reusable plan, maybe from a well-written stored procedure or a properly parameterized query, becomes much harder. Worse, those valuable reusable plans are far more likely to be prematurely kicked out of the cache, evicted, just to make room for yet another unique ad hoc plan that might never be used again. And when those good plans get evicted, the next time they're needed, they also have to be recompiled, adding even more to the overall CPU and time overhead. It's a vicious cycle. Slower query execution, put it all together. You've got memory pressure causing more disk I/O, plus constant high CPU utilization just for compilation. The result, a system-wide slowdown. individual query execution times creep up, users experience higher latency, and the overall capacity of your server to handle concurrent workload, its throughput just plummets. The server feels sluggish, constantly busy, but not actually getting much useful work done.
And you don't have to just guess if this is happening on your server. Your SQL Server instance is practically screaming about it if you know where to listen. You can use SQL Server's built-in dynamic management views, or DMVs. The source specifically calls out sys.dmx cache plans. This DMV lets you peek right inside the plan cache and see what's going on. If you query it and group by the object type column, you can get a breakdown of the types of plans currently stored in memory. You can run a query something like this. Successful select object type, count big as number of plans. Use count big for potentially large numbers. Some cache size in bytes as big int, 1024 as total cache size in B. From sys.mix-plans. Group by object type, order by total cache size MBSC. What you're looking for here is a disproportionately high number of plans where the object type is ad hoc. That signifies plans compiled from standalone batches, often dynamic SQL. You'll likely also see a significant, maybe even dominant total cache size MB associated with those ad hoc plans. This is direct visual evidence, as the source puts it. It's proof that your server's valuable memory and CPU resources are being heavily consumed by caching these non-reusable, often one-time query plans. Plans generated specifically because someone used execute with concatenated literal values. It's often the smoking gun pointing directly to performance degradation caused by this exact anti-pattern. I've personally debugged systems where this ad hoc cache was chewing up gigabytes upon gigabytes of RAM, forcing critical data pages out to slow disk and causing these mysterious crippling slowdowns until we found and refactored the problematic dynamic SQL code.
Right. So we firmly established the severe problems, haven't we? On the one hand, catastrophic SQL injection risk from a security perspective, and on the other, debilitating plan cache bloat from a performance perspective. And crucially, both stemming from the same core mistake, treating user input or variable data as part of the executable code string within an execute statement. So what's the way out? How do you use dynamic SQL safely and efficiently? Well, the answer, as the source material clearly states, is the preferred and fundamentally secure approach, using the system-stored procedure Spexecute. Spexecute is a built-in tool, a system-stored procedure designed specifically for executing dynamic T-SQL statements. Its key difference, its fundamental strength, lies in its explicit support for parameterization. This is the magic word here.
Don't miss out. Smash that like button, subscribe, and explore our other videos in the playlists.